to Joseph Mcguire, because he's going to, and we go first to his faculty advisor, Alex Miller. Please, Dr. Miller, tell us about working with Joseph.
All right, hi everyone. So indeed, I'm here to introduce my student, Joseph Mcguire. So for those of you who don't know me, this is actually my first year as a faculty member at Sonoma State University. And so that means Joe was the first student who I was able to work with for a full year. And I'd like to start by just saying really how lucky I felt to have such a really wonderful first student. So Joe came to me in the fall, right at the beginning of the fall semester, and we decided to do an independent study project where he wanted to just learn what general relativity was. So for those of you who don't know, we just had a talk on special relativity. This is the limit of general relativity where there's no gravity. So the flat space limit of the more general theory, general relativity. And I'd like to say this is a topic that you can get a PhD in physics and never learn general relativity. So the fact that Joe was able to take it on as an undergraduate student is really very impressive. And when I think back to our meetings in the fall semester, I was always so impressed. Every week he would come, ready with interesting questions that really led to fun physics discussions. So I was always very impressed. So then finally in the spring semester, he had learned enough and was ready to take on his own project. And he had done some coding in the past, and so he decided he wanted to numerically solve for the trajectories of particles in black hole spacetimes. And again, I was so impressed that, it feels like it was only a couple weeks in, really early on, he already came to me, having plotted out the trajectory of a particle in a black hole spacetime with his very first solution. And it seemed so quick. But back then, he had just done it in Excel. And since then, he's really solved from first principles, first in MATLAB, and then finally in Mathematica, which everything you'll see today is in Mathematica. And he's then pushed this to more general types of black holes, which he'll tell you about in his talk. But before I let him do that, for those of you who don't know, Joe is going to continue on in his studies. He was accepted into a graduate program at Cal Poly, which is really excellent in mathematics, that is, and he plans to ultimately go on and get a PhD, which will really be great. So congratulations, Joe, on that and on finishing up here at Sonoma State, and thanks again for being such a great first student.
Thank you. Thank you. That was a very good introduction. All right, so welcome everybody. Can everybody hear me all right? Okay. All right, so my name is Joseph Mcguire, and so yeah, I did my project on general relativity in black hole spacetimes, and my great advisor is Dr. Alexandria Miller. All right. So before we really talk about kind of black holes, we really need to kind of understand broadly kind of what general relativity kind of says about the universe. So really kind of the fundamental statement of general relativity is this idea that kind of energy is going to gravity. And so this is energy in all forms. So if you kind of remember the famous equation, E equals mc squared, that kind of relates energy to mass. And so, yeah, so it kind of encompasses all of kind of our picture of gravity in the universe. And so it's worked out to be a very good mathematical description of gravity so far, and it's kind of predicted things that kind of don't exist classically, such as black holes. And so, kind of the defining feature of like black holes is the fact that it's a large mass packed into a very small area. And so, really, kind of in Newtonian mechanics, this isn't really possible. So we really need kind of the framework of general relativity to kind of talk about this. And in particular, kind of talk about how kind of things move around these kind of structures. So one of the major first tests of general relativity was what's called the precession of the orbit of Mercury. And so first of all, precession kind of occurs when you kind of start off with what is initially kind of an elliptical orbit, and it begins to kind of wobble a little bit. And so it's kind of what you see here. So wobble is about a fixed axis somewhere. And so as it turns out, kind of so classical mechanics kind of predicts that all kind of bound orbits will be elliptical. But in the case of Mercury, this isn't quite the case. And so as it turns out, kind of most of this is kind of the pull of other planets and stars and stuff like that. But there's some 45 seconds, arc seconds, that's kind of unaccounted for in mechanics. And so the story goes that when Einstein was able to show that his theory accounted for this 45 seconds, 45 arc seconds, that's kind of a degree measurement that he gave him heart palpitations. Okay, so now that we kind of have this idea that general relativity is a good theory, we kind of want to ask how do things move in general relativity? What's our version of Newton's second law, F equals ma in general relativity? And so this ends up being what we call the geodesic equation. And so ultimately, really what the geodesic equation says is that the acceleration of a test particle, that's this term here, is related to the curvature of a space-time. And so this curvature idea really comes from the fact that we treat kind of in time as dimensions, and we can kind of visualize that as kind of a rubber sheet geometry. And so for the sun, yeah, so these are kind of the different kind of curvatures that we'll end up with for different masses and things like this. So to kind of give you an idea of how dense black holes are really, and kind of how small they are really, if we take the mass of Jupiter, and kind of pack that into, so the kind of defining kind of equation for a black hole, kind of the thing that will kind of give you the radius of this big black sphere that you see is what's called the Schwarzschild radius. And so when we plug this equation into this, when we plug this mass into this equation, this is the gravitational and this is the speed of light, we end up with something that's only about 1 meter small. We have the entire mass of the planet Jupiter packed into a meter. So it's very, 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 very dense. So ultimately, these geodesic equations, these end up being about 4 differential equations, 4 coupled second order differential equations. And so we can kind of solve these numerically, kind of approximate the solutions to these in software such as Mathematica. So everything you'll see from here on out will be plots generated in Mathematica. Excuse me. So black holes are kind of strange objects, but they kind of have 3 kind of intrinsic properties that are kind of nice and classical. These are angular momentum, charge, and mass. And so the mass, so all of these things, if you'll remember, kind of general relativity kind of relates all forms of energy to gravity. And so all of these things will end up affecting gravity in different ways, which is pretty bizarre, as classical mechanics doesn't even only really counts for mass. And so the first kind of solution to Einstein's equation was achieved by Schwarzschild. And so this is the case of a stationary, non-charged, non-rotating black hole. And so this was, so it should be, there's kind of an interesting story here, where Schwarzschild was a German soldier during World War I, and he actually had died posthumously, or the paper was actually published posthumously. He died in the war. Pretty shortly after that came the Reisner-Nordstrom kind of black hole, which is the case of a rotating but a non-rotating but charged black hole. And so then we kind of end up with this 50-year gap, though, in between this charged case but not rotating to this rotating but not charged case. And so we'll get into kind of why this ends up being a more complicated case. But the kind of important thing is that it ends up being a sufficiently complicated kind of solution. And then the most general kind of form of a black hole is the Kerr-Newman black hole, which was derived pretty shortly after that, which is a rotating and charged black hole. So kind of for the case of a stationary black hole, kind of the defining feature of it is called the event horizon. So the event horizon is kind of this point of no return. So it's kind of this point where anything gets trapped in this area, it will get stuck in it, including light. And so really kind of classically, this is kind of bizarre, as light has no matter, it has no mass, and kind of Newtonian gravity kind of relates things, kind of says that it is it's masses that are kind of cause gravitational fields. But because we have this picture of energy causing kind of this gravitational effect, we see that light is actually affected by gravity, just as kind of massive particles are. And so you'll kind of end up with some pretty strange behaviors happening near black holes. And so you'll end up with something that's called a photon kind of sphere. And this occurs when light will enter kind of hit a radius of a black hole in such a way that the light will actually get stuck in a semi-stable orbit around the black hole. And so this kind of leads to really bizarre optical effects occurring, such as if you were to stand at any point in this kind of photon sphere, if you're kind of able to get there and kind of stay stationary, you'd be able to see kind of every single point on that photon sphere. So optically, that'd be pretty bizarre. So when we take the geodesic equations and kind of plug them into Mathematica, these are kind of the equations that we'll end up with. And so kind of the thing to note is that in Newtonian gravity, all kind of orbits, bound orbits, will be defined by ellipses. And so that's what we see here. So with these particles kind of starting off at the same point, the orange orbit here will be the classical orbit, and the blue orbit here will be kind of the relativistic motion. And so what we see is that when we get really close to a black hole, basically that classical mechanics, Newtonian gravity really fails pretty dramatically. And so, yeah, so it kind of shows that we really do need general relativity to talk about motion near these kinds of bodies. And so, but there are some nice features of kind of the motion near these black holes, such as all orbits end up being planar. And so these two end up being, so this is a kind of a front-on view of this motionless particle starting off this position. And this is kind of the side view of the same orbit. And so what we see here is kind of that the particle will stay in the same orbit, kind of stay in the same plane through the black hole. So when we add on this angular momentum term onto kind of the black hole geometry, we kind of get some pretty dramatic differences from the stationary case. And so what we end up with are, so you can kind of see it in this picture here. So this is the, so these are going to be the different surfaces that you end up having in a curved black hole, kind of evolving with the angular momentum. And so, yeah, so the kind of green sphere that you see here is the event horizon that we saw from Schwarzschild. This blue sphere that just passed is going to be what's called the inner horizon. Kind of the outer horizon kind of ends up being the more important surface, as it has the property of if you get inside of it, you can't escape it, just like Schwarzschild. But then we get this odd region that doesn't exist, kind of exists solely because of the angular momentum in the black hole, which is called the ergo region. And so the ergo region is going to be defined by this kind of red sphere out here and this kind of red conic section on the inside. And so if you get inside of this region, kind of between these two surfaces, you're going to, the kind of rotational effect of the black hole is kind of so strong that you can't really stand still anymore. You can, you have to kind of rotate with the black hole. And so this kind of also acts as an event horizon for massive particles near the black hole. As if you have any kind of mass, you'll get stuck in this region, kind of get sucked into the black hole. But in the ergo region, things like light can still escape. And so kind of an interesting note here too is that this actually ends up being kind of the most applicable case of kind of black hole spacetimes, kind of black hole geometries, because kind of the charge per mass ratio for most celestial bodies, kind of astronomical bodies, will kind of end up being negligible. So, but we do end up with some things that have high kind of spin ratios compared to their mass, such as neutron stars. Okay. So when we, so through Mathematica, we can kind of plot the motion of particles in this kind of rotating black hole case. And so there are some things that are kind of preserved from Schwarzschild. So if you start off in the equatorial plane of this black hole, you'll end up with planar motion still. So as we see here, this is kind of top-down view. This is kind of a side view. And it kind of stays in the same kind of plane of motion. And so I should say too that any kind of, kind of in Newtonian gravity, angular momentum of a body doesn't really affect gravity at all. It's really just the mass that affects things. And so it's kind of bizarre that we see that the actual spin of the black hole will kind of deviate how things move near it too. So that's kind of an odd behavior that we see. Additionally, so if you get off the equatorial plane though, things no longer remain planar. So as you see here, if we start a particle and kind of project it downwards, it's going to kind of precess about kind of the horizontal axis, which is pretty strange. So additionally, there's this factor of kind of the rotation of the black hole. And so the rotation of the black hole kind of dictates how stuff will move. So how the particle is moving relative to the rotation will actually affect how the particle moves. And so what I mean by this is that this black hole is spinning in a clockwise direction, so kind of this direction. And so we take the same particle, or kind of the same mass particle and same position, and we project it in opposite directions. And so what we end up with is kind of a weaker, kind of smoother gravitational field here, while in the kind of the opposite direction of how the black hole is rotating, we're going to end up with pretty strong kind of gravitational effects here. And so this is kind of caused by something called frame dragging. And so really the idea behind frame dragging is that if you have something that has sufficiently high mass, it's going to, and it's spinning, it's actually going to affect the kind of geometry around it. And that's going to affect kind of the gravitational field around it. And so you end up with some pretty strange things such as, so kind of how the particle is moving against it or with the black hole kind of affects how the particle will move. And yeah, so this graph to the left right here is going to be for a high charge black hole. So this is Kernel, where we have a charged and rotating black hole. And so we have a high charge here, and we're kind of evolving it with the angular momentum. And so these are kind of the same surfaces that we saw in Kerr, except they're kind of deviated in kind of a more, the conical section is kind of flattened out a little bit, and the radiuses are kind of smoother. And so this kind of ends up being the most general case of a black hole, as you have a charge, kind of mass, you have charge, and you have rotating energy. But as it kind of turns out, there's nothing really that has a high charge per mass ratio that we've seen empirically, especially on that astronomical scale. And yeah, so it actually ends up being that Kerr is kind of our best applicable model to use. So as far as future work goes, it'd be kind of neat. It'd be kind of neat to kind of see these things, kind of like visual, as Chris's project kind of showed, kind of a visual representation of some of these things. Kind of solve for Kerr-Newman or Reisner-Nordstrom trajectories. So we just solve for Kerr and the Schwarzschild trajectories. Additionally, Kerr-Newman has the potential of kind of adding in a magnetic monopole, so it might be interesting to see kind of how that affects things. And study the thermodynamic properties of Kern-Newman. So I just really want to say thank you to my advisor. You've been so supportive and so helpful like past year. Really appreciated it. I don't want to thank him. I wouldn't be here if it wasn't for the many classes I took with Dr. Shi. And I'd like to thank the Math and Stats department. Really, you guys have been fantastic. 4 years ago, I was feeling Calc 2 and really considering dropping out of college. And here I am graduating with 2 bachelor's degrees and going on to a master's program. And really, I'd like to thank all my family and friends and everything. You guys made it possible. I really wouldn't have been made it this far without you guys. And thank you.
Well, thank you so much, Joseph. Once again, a big round of applause here. That was fantastic. Oh, the last one. There's some. Yeah, my Robert Wald is my was my quantum professor in grad school, so that's good to see. I'm gonna steal the first question just because it's so fascinating. You've put a lot of work in throughout the semester and the year, as we heard from Alex, but there's also things have kind of started to explode the number of visualizations you've had. Can you talk a little bit about the process of what it was like to get to a point where you started exploring these black hole models in so much more detail, and how it kind of was built on the earlier computer work?
Yeah, so as Dr. Miller mentioned, I had started with like Excel, kind of just like verify some like computational stuff. So I started working in a MATLAB. I worked in it previously, and it's more like a programmer's programming language. But then we only switched over to Mathematica like in the past few months or so. I mostly did this because we kind of end up with some nice like visual representations of stuff like all this that you're seeing. And you can do that in MATLAB. It's just not the easiest. And so really the work of the project and stuff has been getting this stuff working, and attempting to get some. I put a lot of work into trying to get a Kernel to work, and not end up working out. But yeah, I've spent a lot of time trying to get those visual representations working.
Well, I just wanted to say congratulations. I want those the talk, or just for the videos, for showing frame dragging, having those two particles go in with the two opposite rotations. That was really good. I've not seen it so clearly demonstrated, and getting a sense of frame dragging. Okay, opening it up to the broader community. A thumbs up here, and or a wave of hand. I'll call on you to ask a question. I'm seeing there's no mic. Do you have something that that you could type in the chat box? Let's look for another question. Or has the mere level of the conversation, maybe Sam, I'm seeing there. Do you want to ask oh no, very good, Christopher.
Yeah, so you might not know, but I just heard you mention magnetic monopole. So I was wondering if you could touch on that just like slightly. Because I just want to know what kind of work has been put into that. Like, again, you might have no clue, which is totally fine, but I just heard those two words together, and I was like, wait a minute, that's not right.
No, I'm really glad. Yeah, I'm glad you asked. No, I actually put a lot of work in trying to get that working. So really empirically, like there's no reason when we think that like that might exist for black holes. It's kind of just like in the most general case, like you kind of want to include magnetic monopoles, just because we're pretty sure that macroscopically they don't exist, but like black holes could be microscopic in some way, so it's possible that there might be a strange experiment or something one day that finds that there's a very small thing that can be modeled as a monopole. But yeah, I think when you do that with this, you end up with some even stranger orbits. Yeah.
All right, awesome. Thank you.
Sam, you do have a question. Ask a question. I'm just, by the way, we have a fantastic one of our annual newsletters, which I will send out as an email to the students, but I am going to see if I can get it up online and put a URL in the chat box if people would like that. So while I do that and Sam asks the question, maybe Alex, you could serve as moderator while I try to handle this task. Okay, take it away, Sam.
Thank you. So Joe, I don't know much about general relativity, but I always thought, I've seen the models where it's like a heavy object pulling down a rubber sheet, and that causes, the gravity is actually caused by the deformation of space. But I think you said the orbit of Mercury is more accurately predicted by the general relativity than the Newtonian model. And so what account for the difference? I thought it was just a different way of looking at the same phenomena, but I didn't realize that the prediction of the orbits would be changed. I thought just the fabric of space would be bent by the mass of objects. So what accounts for the difference in the orbit? Yeah, so there's so as I said, like most of it's accounted for by a kind of classical. So really it's not 100% accurate to say all classical orbits are like ellipses usually.
you do end up with like, if you have poles on, if you have a bunch of like planets like you do with Mercury, and like they kind of pull on it, and so it's, yeah, that accounts for most of the kind of precession. But so kind of there's this like extra like 45 arc seconds that kind of that we see with the precession. And so kind of the reason for this is that this is kind of the relativistic. So when you get, so really like at pretty far distances, like classical mechanics is totally fine with describing most movement. But because Mercury is so close to the sun, you start so it's like 45 arc seconds, so it's very minuscule, but it's still kind of close enough to have kind of a relativistic pull on it. And that's caused by, I think, so that's caused by I think it might be kind of what's the name of it? But there's a particular kind of force in general relativity that kind of, or not force, but there's an effect that kind of accounts for this. I don't know if I answered your question, Dr. Brandon.
No, thank you. And I'm sure it's really complicated. I guess the relativistic effects are just stronger when you're closer. So I guess there's just more distortion of space-time than is accounted for in the Newtonian model or something. I don't know. I don't even know what I'm saying. So thank you.
Yeah. Thank you for the question.
I think, Joe, we have a question in the chat if you want to answer that one about, I don't know if you want to read it or I can read it.
Sorry, I'm trying to pull up the chat.
It says, can you comment on what thermodynamic studies are you most interested in for the Kerr-Newman that you mentioned in your future work? And that comes from Addie, or sorry, AD, I'm not sure.
Yep, I think it's Addie. It's a good question. So like there's this phenomena that actually Stephen Hawking like derived, that you end up with some kind of net energy flux across the event horizon. And so really this is kind of Dr. Miller would know a lot more about this, where you end up with some, it's basically possibly a quantum effect. And so we know really well how that works in like Schwarzschild. I just haven't studied really well how that works in like Kerr-Newman. And so like the idea is that you have energy crossing the event horizon, which is pretty bizarre because it's supposed to be this area of no return, but we have something basically coming off of it, which is pretty strange. And that thing being kind of entropy, which is then kind of related to temperature and things like that.
Great. So are there any other questions? I don't know if I have to scroll to see if there are any thumbs up. All right. Well, I think, I don't know, Tom, if you want to, or do you have closing statements? I'll just say great job again, Joe. Excellent.
Thank you everybody for coming. I really appreciate it.